Good morning to everyone. My name is Conrado Afonso, and I would like to thank very much the organizers of THERMEC 2021 and the Technical University of Graz in the name of Professor Sergio Amancio for the invitation to present this work, which title is Chemical and Nanoscale Orientation Mapping, Characterization of Nanostructures in Beta Titanium Advanced Alloys and Interfaces. I am from the Department of Material Engineering at UFSCar, São Carlos, São Paulo, Brazil. And I would like to mention that our Materials Engineering course, which is the first one in Brazil, in Latin America, completed last year 50 years. So we completed as well 50 years of material science engineering in Brazil. So I would like to present this work, which is based mainly in the characterization technique, which is called ASTAR, which is the brand, and the technique is the ACOM, which is automatic crystallization orientation mapping. So we get a lot of nanobeam diffraction patterns corrected by precession electron diffraction. And we collected those nanobeam diffraction patterns in step size in the order of 5 nanometers, can be a little bit more or less. And we map the crystallography of nanostructures. So samples processed by severe plastic deformation, nanocrystalline alloys in general. So we have this equipment installed in our microscopy lab in a TAM bag from FEI. It's a 200 kV microscope. We can use both the Lab 6 gun and the field emission gun in another microscope as well, this one here. Okay, so it's a powerful characterization tool in order to do this orientation mappings in nanoscale. Okay, and another place that I used this kind of technique was in Universidad Politécnica de Valencia, in Valencia, Spain, and I used it a lot there as well, a dual beam microscope in order to prepare the TAM samples by FIB, by focused ion beam, which is very useful in the case of interfaces and very localized samples. So the first work that I would like to present to you in this general theme of the presentation is this work related with the powder metallurgy beta titanium alloy. So it's a porous sample which was processed through high pressure torsion. So it was a work in collaboration with Professor Amigo of Valencia and professors from Russia. Okay, so this work was recently published in scientific reports in 2017. It's a related work, and I would like just to show the graphical abstract of this work. So we were going to convert a powder metallurgy sample with around 5 to 10% porosity in just one step to a dense sample, and at the same time with a nanocrystalline structure by Hpt. So this is just a resume of the results obtained that I'm going to show as follows. Here is the SEM images in backscatter sign, in backscatter mode of different alloys that we studied in this work. So titanium niobium tantalum alloy, and 3 different additions of iron, 1.5, 3, and 4.5 iron weight %. So we can see that we can have some niobium, which are those white spots, which are not completely undissolved, are not completely dissolved. They are microstructure during the sinterization step. Depending on the alloy and the composition, we can have a better distribution of this niobium and the beta stabilizing elements. And due to addition of iron, we can see that the porosity increased. The porosity increased in the alloys. Okay. Here is the X-ray diffraction of all the powder metallurgy samples. So the first one, the blue here, is the titanium niobium tantalum without iron, and the 3 additions of iron. And we can see that the alpha peaks, they decrease, they remain just a very slight peak of alpha phase. So the addition of iron led to the better stabilization of the beta phase. Because in the end of sinterization process, the sample is furnace cooled. So it's a very slow cooling after the powder metallurgy process. Some properties of this material by powder metallurgy. We have 5% porosity for titanium niobium tantalum alloy, and increasing the iron content, we can see that there is an increase in the porosity. And regarding the percentage of beta phase, without iron, we have almost 20% of alpha phase, and the remaining is just beta phase. And with the addition of iron, we decrease significantly the fraction of alpha phase. So the iron increases a lot the stabilization of beta phase. And here, the mechanical properties and the elastic modulus, that sometimes is called to be a physical property, and which was measured by flexural strength. And we obtained the lowest value of elastic modulus for the alloy without iron, 74 gigapascal, and increased a little bit the elastic modulus with the addition of iron. And now we have the results of 2 alloys. We select just 2 alloys, one without iron and another one with 3% iron addition. We have both PM samples, so before the severe plastic deformation, and both after HPT. So we can see that after HPT, which are the blue and red curves, we can see that there is a decrease of the beta peaks, which can denote that we reduced significantly the grain size of these materials. So we can check this in the results that I'm going to show next. And here the parameters of the HPT, which was 5 turns and a pressure of 6 gigapascal. And here we have the TAM conventional analysis of both alloys. First here the alloy without iron and the alloy with iron addition. So we can see for the alloy without iron, there's the titanium niobium tantalum. We have mostly beta phase, but we have some omega nanoscale precipitation. So we can see here in the select electron diffraction, the orientation relationship between the beta phase and the omega phase. And the brighter spots are more intense from beta phase, and those orientation relationships with the omega spots, which is a common electron diffraction in the 110 of beta phase. The same orientation for the alloy with iron addition, and we can see that the omega phase is much smaller. Because of this, we have a diffuse appearing here of the omega spots. Okay. And we did the ASTAR analysis, the orientation mapping in nanoscale. We can see here the reference bar of 500 nanometers, and we can see that we can characterize, we can identify very small needles of alpha phase, nanoscale, and very small needles of alpha phase. So here we can see how useful is the technique of ASTAR. In the left, we have the virtual bright field image, and on the right, we have the phases image. In red, we have the beta titanium matrix. In green, we have the alpha left here. Okay. And after the HPT process, we have here just a conventional TAM image in bright field. So it's very difficult to identify clearly the domains of the beta titanium grains. So it's very difficult to see all the grain boundaries and determine exactly which is the grain size of this sample in the conventional TAM image. And here, the electron diffraction of rings, denoting that we have a nanocrystalline sample after the HPT. This is the sample, just titanium niobium tantalum alloy. Okay? So in order to confirm the nanocrystalline origin of this structure after HPT and determine the grain sizing as well, we did the ASTAR analysis again in order to do the orientation mapping by crystallography. And we determined here in a low mag image, the nanoscale grains of beta phase, which is a softer phase. And here the harder alpha phase that decreased as well the grain size, but not as much as the beta phase. And here we can see the very small size of the beta titanium grains. So in a more detailed image, in higher magnification, we can see here more or less the size, the grain size of the beta phase. An example, as an example of the previous image, a little bit bigger particle of the alpha titanium phase remaining in the structure. So here is the phase map, and the image in the left, the bottom part, is what we call the, here we have the virtual bright field, and here at the bottom we have the virtual dark field. So we can see that we still have some omega phase precipitates in nanoscale. Okay. Now I'm going to show some results of the Hpt samples. So for the alloy without iron, we had a porosity of 5% after Hpt is reduced to significantly to 0. So we killed all the porosity in this alloy. The grain size was 45 microns before Hpt, and after Hpt around 50 nanometers. So we reduced it 3 orders of magnitude, the grain size of the alloy. And for the alloy with iron, we have a porosity of 9 that went to 0 as well, and a grain size of 16 microns that went to 17 nanometers. So we measured the elastic modulus and hardness by nano hardness, and we reached here the values which increased the value of the nano hardness after the Hpt for both alloys, and the elastic modulus decreased for most of the results obtained. So we had here from 80 to 100 gigapascal, and after Hpt, we obtained some values smaller, such as the 79 gigapascal for the alloy without iron. Okay, so there was an increase in the hardness and a decrease in the elastic modulus due to the obtaining of a nanostructure. Okay, so here I would like to show a brief work realized recently. So it was in collaboration with Professor Rubens Caram at Unicamp in Campinas in Brazil, and her PhD student Marina Gerardi. And it was a work realized in Brazilian nanotechnology laboratory, and we used a Titan microscope that they acquired recently, which is an incredible machine with 300 kV and CS corrected, and can reach a resolution of 0.6 angstroms or 60 picometers. So it's an incredible microscope, and we try to use in the characterization of a beta titanium alloy, titanium, 13 molybdenum, 2 iron alloy. Okay. And here I present the beta titanium alloy in higher magnification. So we can see here the scale of 10 nanometers, and we are imaging here the omega phase. So we can see the distribution of the alloying elements. Just a second. And as we can see here, the omega phase, which is a precursor for the precipitation of alpha phase, is titanium rich, while the beta stabilizing elements, the iron and molybdenum, are rejected to the beta titanium matrix. So it was easy to see this chemical mapping using the EDS in the Titan with the chemistane, which is composed by 4 EDS detectors. So they increase a lot the signal of the EDS, even in a very thin sample in nanoscale, and increasing even more the magnification. So we are here in a high resolution stain image. We can see here from the reference bar of 2 nanometers, So we are inside the same nanostructure that we saw in the previous image. So we have, besides the omega phase, we have in a deeper magnification, we have the phase separation in a beta and beta prime phase. And we can see that the beta prime phase is richer in heavier Z number elements, such as molybdenum and iron. Even that is not very clear here in the chemical mapping, we can see that we have the spinodal decomposition, which is a slightly variation of the composition of titanium in the darker regions, and increasing the percentage here from the intensity in the image in the brighter regions of the beta rich phase separated. Okay, so the conclusion of this work, which is ongoing, is that the Z contrast images in nanoscale for the omega phase and the phase separation is very effective in order to map chemical distribution of beta stabilizing alloying elements to the beta titanium matrix. And the X-ray elemental mapping through EDS, the ChemStan, used in a CS-corrected Titan microscope, can provide a nanoscale chemical mapping of phase separation through spinodal decomposition in beta titanium alloys. And the last part of this work that I would like to present is the star characterization of thin films in binary titanium niobium alloys produced by magnetic sputtering coatings over stainless steel substrates for biomedical applications. So this is a work of a PhD student, David Gonzalez, which is from our university as well, our graduation program in material science and engineering. So here, the results, some main results of the characterization for all the alloys, the X-ray diffraction of the thin films. For all the compositions, we obtained just beta phase, since the 59% atomic. And we have a work published recently regarding this study. And here we have a graph showing the hardness with the increasing of niobium and the elastic modulus. And we can see that we obtained the lowest values of hardness and modulus for the lower addition of niobium, 15%, and higher addition of niobium, 40%. Okay? And we did the characterization, just the EDS X-ray mapping of the elements. So the thin film is mainly composed by titanium niobium, and at the bottom part we can see the composition of the stainless steel, the iron and chromium composition. And here is just a stem image in dark field showing the general nanostructure of this thin film. And here, first showing the titanium niobium thin film with 15% of niobium, and we can see a general TAM image of the nanostructure. And here we see already the star results. So we have the mapping of the nanograins, which are elongated grains, and mostly an orientation in one texture, in one direction, one crystallographic direction that I will show you soon. Okay, and here we can see one map in lower magnification, showing the nanoscale of these elongated beta grains. And here in the tail, near the stainless steel substrate, we can see that we have a transition in the growth mode of the grains produced by magnetic sputtering. So here we have a more almost X-axis grains, and then we have a transition to more elongated grains in the later stages of the thin film growth. So this is already the results for the titanium alloy with 20% atomic of niobium. Here the alloy with 30% niobium, and we can see that we don't have that transition, we just have the elongated grains. And here the map of the beta phase and map of the iron austenite from the stainless steel. And here we have just one TAM image of the film in bright field mode. And And on the right, we have a dark field mode TAM image, showing that we have we still have some omega phase precipitation, although the thin film was produced by magnetosputtering, which is a completely different way of growth of the grains. We still have the omega phase appearing in one of the compositions. And finally, here for the titanium niobium 40 atomic percent, we have as well the V grains, which is the shape of an elongated V grain for those thin films. And here, regarding texture, so we have the projection of 4 alloys in the x-axis. So we can see here that we have some texture for the higher niobium alloys, and the y-axis and z-axis, showing that depending on the composition, we have different types of textures. So here, I leave you the conclusions of this work. Okay. And I would like to thank very much again the organizers of THERMEC and the CNPq and FAPES from Brazil, and UFSCar, and all the financial support for the realization of this work. So thank you very much for your attention.